let's do the last problem in that last video again. It said f of x equals 1 minus x to the minus 2. And let's look at the patterns this time. So we have negative 2 times 1 minus x to the negative 3 times negative 1. So it becomes a positive 2. We can take that out. We can go with it that way. Then the second derivative, we multiply negative 3 times 2, 1 minus x to the minus 4 times negative 1. And again, we can make it a positive. And then the third derivative, we have negative 4 times 3 times 2 times 1 minus x to the minus 5. And again, we can make it a positive because this chain rule negative 1. And the fourth derivative of x would be negative 5 times 4 times 3 times 2 times 1 minus x to the negative 6. And our negative 1 turns to positive. So you can see the nth derivative here because that's going to be very helpful in the future. Here I have n plus 1 because 4 factorial would be 4 times 3 times 2. So 5 factorial is 5 times 4 times 3 times 2. Now go back to here. My third factorial would be 3 times 2. 3 factorial would be 3 times 2 times 1. But 3 plus 1 is 4 factorial. So that's n plus 1 factorial. So let's call this n plus 1 factorial. And then we have 1 minus x. And here we have the derivative. Actually, it starts off with a negative 2. And then we subtract 1 every time. So we have negative 2. And then at 1 we have negative 3. And at 2 we have negative 4. So do you see that this could be negative 2 minus n? We could also call it negative n minus 2. So our power down here would be negative n minus 2. So that gives us our nth derivative, which is going to be easy. And then we found f of 0 to be 1 and f prime of 0 to be 2 and f double prime of 0 to be 3 times 2. Notice that we're looking at the patterns. And the third derivative is 4 times 3 times 2. And the fourth derivative, of 0 is 5 times 4 times 3 times 2. Which then we can say the nth derivative at 0 is n plus 1 factorial. So then if you take these two things, notice if you put a 0 for x, then here we have 1 minus 0, which is 1 to any power is 1. So these two now are equivalent values. So we have the summation from n equals 0 to infinity. And our Maclaurin series says the nth derivative at 0 over n factorial times x to the n. So let's plug in our nth derivative at 0 to be n plus 1 factorial. So that means we have the sum from n equals 0 to infinity. And here we have n plus 1 factorial over n factorial x to the n. Now remember, n plus 1 factorial is simply the series from 0 to infinity. And we have n plus 1 times n factorial over n factorial x to the n. So that gives us the series from n equals 0 to infinity. And we have n plus 1 times x to the n. Not just n, x to the n. That's what we ended up with before, but if you can look at the patterns, that's really where you need to be headed with these. And so let's look at another one. So the next problem says find Maclaurin series for f of x equals sine x. Now remember, this is what our Maclaurin series looks like, so this is our goal here underneath. And remember, we start with derivatives. So we have f of x equals sine x. And then f prime of x, what's our derivative of sine? Cosine of x. Good. So the second derivative, what's the derivative of cosine? It's negative sine x. And the third derivative is negative cosine x. And the fourth derivative is positive sine x. So you're back to the beginning. So it makes a cycle. So our problem here is that you can't find the nth derivative of f because it depends upon where you stop. Because it's cyclic. It says sine, cosine, negative cosine. So the next step is to look at 0. So f of 0 means sine of 0 is 0. And then cosine of 0 is 1. And then sine of 0 is 0. Doesn't matter about the negative out there. Second derivative. Third derivative. The cosine of 0 is 1, and there's a negative, so negative 1. The fourth derivative at 0 is 0. Sine of 0 is 0. Now again, we can't find our nth derivative because it depends upon where we stop. But let's look at this term by term and see what we can do there. So we know that we have the series n equals 0 to infinity is the nth derivative of f at 0 over n factorial times x to the n. So let's write out the terms. And this would be f of 0 plus f prime of 0 times x plus f double prime at 0 over 2 factorial times x squared plus the third derivative at 0 over 3 factorial times x to the third. We might as well do the fourth because we have that there. So let's fill these in. This means we have 0 plus the first derivative at 0 is 1 times x plus the second derivative is 0 plus the third derivative is actually negative 1 over 3 factorial x to the third, plus the fourth derivative is 0. Let's fill in the fifth derivative. Let's go back. The fifth derivative of x is positive cosine x. So the fifth derivative at 0 is 1. So our fifth derivative would be positive 1 over 5 factorial x to the fifth. So that should be enough to help us establish a pattern. But let's look at a couple more terms. The sixth derivative of x would be negative sine x. And the seventh derivative of x would be negative cosine x. So if we were to erase this and continue with our pattern, for our sixth term, the sixth derivative, sine of 0 is 0. And then the seventh term would be negative 1 over 7 factorial x to the seventh. I think we have enough for a pattern, definitely this time. So this means I have x minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh. So we could write our power series based on that. Before we continue, go back and look at these terms. Here we have a 0 and then a 1, a 0, a negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1. So that kind of gives you the hint. There's no F, you have to look at it term by term on this case. So now let's see if we can write this as a series. Let's say the series from n equals 0 to infinity. Now we see it's alternating, so let's put negative 1. Does it start positive or negative? It starts positive, so let's put an n here. And then let's look at our powers of x. So we have x to the first, and then we jump 2, so that means 2n. But to start at 1, we have plus 1. And then we have the same number down here, factorial. So let's check what we have here. It feels right, but if you let n equal 0, we have x to the first. If you let n equal 1, it's negative. And on the numerator, we have x to the 2 plus 1, which is 3. And then 3 factorial in the denominator. So this is our definite representation for sine of x. So now what we need to talk about is our radius of convergence. So let's do the ratio test. The ratio test will become your best friend if it hasn't already. So we have the limit as n approaches as n approaches infinity. Don't know what was going on there. So we have negative 1 to the n plus 1, x to the 2n plus 1 plus 1 over 2 n plus 1 plus 1 factorial. And then in the denominator, we have negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So then we have the limit as n approaches infinity. Negative 1 to the n, negative 1, because that makes negative 1 to the n plus 1. And then we have x to the 2n, and that's 2n plus 1 is x to the third. Maybe we shouldn't skip that step. This power right here, let's do it this way. This power right here becomes 2n plus 2 plus 1, which is 2n plus 3. That's what the margin of your paper is for, to do those little calculations there. So then we have x to the third here. And in the denominator, guess we could have worked it out there. We have 2n plus 3 factorial times. So we multiply now. And in the numerator, we have the 2n plus 1 factorial. And in the denominator, we have negative 1 to the n, x to the 2n, x to the 1. We could have left the other one, x to the 2n plus 1, but there we go. Those cancel. This cancels here, but we're left with an x squared. There's one left. We only took away one of those. These cancel. But it's absolute value, so that doesn't matter. So what we have now is we have the limit as n approaches infinity. The absolute value of negative 1 is 1. So we have 2n plus 1 factorial times x squared over 2n plus 3 factorial. This means 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. It's going to work out nicely for us, isn't it? So these cancel now. Remember, x squared is always positive. So we have the limit as n approaches infinity. And n's are positive, so now we have x squared over these two. You have a couple ways to do it. Let's leave them like they are. 2n plus 3 times 2n plus 2. And the reason for that is it's infinity times infinity, which is infinity. So I have x squared over infinity, which equals 0, which is less than 1. So we have convergent for all x. So our radius of convergence is infinity. So we can come back up here and we can say, out of space, we can say that sine of x, let's do it a little nicer. Let's say f of x equals sine x can be represented by the series n equals 0 to infinity. We have negative 1 to the n, and then we have x to the 2n plus 1 over 2n plus 1 factorial, where r equals infinity. So our radius of convergence is infinity, and our interval of convergence is negative infinity to infinity, so we can say for all x. So the next problem says, think about the Maclaurin series for cosine of x. So think about the fact that f of x of cosine of x really is equal to the derivative of sine of x, which is really awesome because we already know sine of x. Sine of x is that Maclaurin series we just did. So it says the sum from n equals 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Now that's the long way around. Let's look at it term by term. So we had x minus x to the third over 3 factorial plus, they're the odd ones, x to the fifth over 5 factorial minus x to the 7th over 7 factorial, and so forth. So if we take the derivative of the first term, we get 1 minus the derivative of x to the of this next term becomes 3 times x squared over 3 factorial plus 5 times x to the fourth over 5 factorial minus 7 times x to the 7th over 7 factorial plus so forth. Now, 3 times 3 in this 3 factorial, this 3 factorial down here means 3 times 2 times 1. So these cancel. And this is 5 times 4 times 3 times 2 times 1. So these cancel. So let's look at this. It means 1 minus x squared over, how about if we call that 2 factorial, plus x to the fourth over, hopefully you see the 4 factorial, minus, oh, that should be a 6, x to the sixth over 6 factorial. Now, do you see the pattern there? And that's how we build the cosine. Now, since sine converges for all x, remember the derivative also has the same radius, so the radius of convergence here is infinity. So we say that f of x equals, oh, we didn't write it as a power series. I'm sorry, let's go back. So this equals the series, and we start with n equals 0 to infinity. It is alternating. The first term is positive, so let's try an n there. And then when n equals 1, it's negative, so that's true. When n equals 2, it's positive. And then we have x to the, we're moving up by 2 every time, so this would be 2n. And then in the denominator, we have 2n factorial. We know that r equals infinity because it's the same for an original function and its derivative. So we can say for all x. So we can pick any x that we want to, and the r is infinity. Hopefully that one makes sense to you. Let's use that now, and the directions say find the Maclaurin series. F of x equals x cosine x. Now we just found the cosine of x. If f of x equals cosine of x, then it can be written as the series from n equals 0 to infinity of negative 1 to the n x to the 2n over 2n factorial. So what we have here is we have an x times that. So f of x equals x cosine x, which equals x times the series from n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. X is not dependent on n, so we can move it inside. So we have negative 1 to the n, x to the 2n plus 1. X times x becomes x to the 2n plus 1, and over 2n factorial. And our r stays the same, so this is for all x. Let's do it that way. That's in parentheses for all x. Let's look at f of x equals 1 over 1 minus x. We know this is the power series of x to the n, where n equals 0 to infinity. And so we don't really have to change that. Just keep that in mind. And that was 1 plus x squared plus x to the third. And it had a radius of 1. So let's go back and let's pick up another one. Let's talk about f of x equals ln of 1 plus x. So the first derivative, remember that if we're going to do a Taylor-Maclaurin series, we're doing Maclaurin, then our first job is to take the derivative. So that would be 1 plus 1 over x. So let's call that 1 plus x to the negative 1. And then the second derivative would be negative 1 plus x to the negative 2. And the third derivative would be negative 2 times negative 1, which is 2, times 1 plus x to the minus 3. And the fourth derivative would be negative 3 times 2, 1 plus x to the minus 4. Remember, you're looking for patterns. And the fifth derivative of x would be positive 4 times 3 times 2 times 1 plus x to the minus 5th. Let's do one more. The sixth derivative of x would be negative 5 times 4 times 3 times 2 times 1 plus x to the minus 6th. So this means our nth derivative of x. Now notice it's 1 less every time. So we have a negative 1. It's alternating. So we have a negative 1. And we really want to look like here. On the second term it's negative. And on the third term it's positive. So with that in mind, the third term is positive. So let's do an n minus 1. You can go n plus 1 or n minus 1. Most people go to n minus 1. And then we have factorial. Here we have 1. In the first one we have 1. In the second derivative we have 1. In the third derivative we have 2. In the fourth derivative we have 3 times 2. In the fifth derivative we have 4 times 3 times 2. So if you look at those, we have n minus 1 factorial here. And then we have 1 plus x. And if you look at the powers, on the second derivative we have negative 2, and on the third derivative we have negative 3. And on the fourth derivative we have negative 4. And on the fifth derivative we have negative 5. So here we have negative n. So now let's look at derivatives. F of 0. Natural log of 1 is 0. The first derivative, we have 1 to any power is 1. The second derivative, we have negative 1, and 1 to any power is 1. The third derivative, we have 2. The fourth derivative, we have negative 3 times 2. The fifth derivative, we have 4 times 3 times 2. The sixth derivative, we have negative 5 times 4 times 3 times 2. So we've kind of already established that pattern. So we can say that the nth derivative at 0 is negative 1 to the n minus 1. And then here we have n minus 1 factorial. So let's put that into our Maclaurin series. Can't scroll. Let's put that into our Maclaurin series. We know that it's n equals 0 to infinity. The nth derivative at 0 over n factorial times x to the n. So we have the series from n equals 0 to infinity. Now the nth derivative is negative 1 to the n minus 1. And then we have n minus 1 factorial over n factorial x to the n. Now, n minus 1 factorial, so we have negative 1 to the n minus 1. So this is n minus 1 factorial, but the denominator could be n times n minus 1 factorial. So these are going to cancel out right there. We have x to the n. So that means our series is the series from n equals 0 to infinity, negative 1 to the n minus 1. And then we have x to the n over n. And that's where that series comes from. So this is, let's go down here and say that this was f of x equals natural log of 1 plus x. So there are some standard, there's a chart that gives us our important Maclaurin series and the radii of convergence. Now in this one we could do the ratio test. So we have the limit as n approaches infinity. We have negative 1 to the n plus 1 minus 1 becomes n. X to the n plus 1 over n plus 1 all over negative 1 to the n minus 1. X to the n over n. So we have the limit as n approaches infinity. Negative 1 to the n minus 1 times negative 1. Can we just leave it as n? X to the n, x to the first over n plus 1 times negative 1 to the n minus 1, x to the n over n becomes on top. So these x's cancel. Most of these cancel, but what doesn't cancel is in absolute value bars. So we have the limit as n approaches infinity. We technically have negative 1 on top, and then we have an n and we have an x over n plus 1. But this negative 1 becomes a positive 1 because you're an absolute value. So let's use L'Hopital's rule, or divide by the highest power of n in the denominator. So we have the limit as n approaches infinity of the absolute value of x, which is less than 1. So our radius is 1. So this function can be represented by this Maclaurin series, and the radius is 1. Here we have some important Maclaurin series and the radii of convergence. We've done most of these. We haven't done the inverse tangent or the 1 plus x to the k. They will happen in the next video. The 1 plus x to the k is where the binomial theorem comes from. And this right here, this kn, is combinations. It's n items chosen k at a time from permutations and combinations that we learn in probability. So you should make a note of these, screenshot, take a picture, and we'll pick this up in the next video. Thank you.